already covered pretty much next class's material. So is there anything that you would like to discuss from what we've talked about so far? Otherwise, I have this nice movie that somebody made for their master's thesis back in Ohio when I was a professor, that illustrates the effects of special relativity quite nicely. So we'll watch probably the first 10-15 minutes of it today, and then the rest after probably in 2 or 3 weeks. So anything else we should talk about before we? Yeah. Fine.
Notice how the farther away they are, the longer it delaying the moment at which we see them move. For example, this clock is 30 meters away. So, remembering that light now travels 10 meters per second, it displays a time 3 seconds behind our own. The apparent disagreement between the dashboard clock and any other clock is simply related to its distance away from us. The disagreement is least for the closest clock, the one on our left. We will take a short trip, and as we do, watch the outside clocks, taking particular note of how fast or slow their hands appear to be moving. At a modest 27 kilometers per hour, where meter is 0.75, or 3/4 the speed of light, the exterior clocks appear to be running faster than normal. Stopping briefly at the end of the track, we see that the closest clocks are about 7 seconds ahead of our clock, so our dashboard clock is no longer synchronized with the exterior clocks. As we shift into reverse, notice how different the clocks look when they're receding from us. We don't appear to be going so fast this time, but we're still going at the same speed, 27 kilometers per hour. Moreover, the clocks appear to be running slow. Back at the start, let us check the clocks again. The image of the clock that is 30 meters away is now 11 seconds ahead of our clock. Taking into account the light's 3-second travel time, we discover that the clock is actually 14 seconds ahead of our dashboard clock. So someone standing outside has actually experienced more time than we have. Let's repeat the experiment, but this time we'll concentrate on that one clock and on our own. To help us compare the two, we'll use an instrument, a delta clock, which shows the difference between the two clocks' apparent times. It currently registers negative 3 seconds because the exterior clock is 3 seconds behind our clock. As soon as we start to move, this difference changes. The exterior clock gains as we approach, and this time we turn to keep it in sight, it loses as we recede. The stripes across the rear window are just the rear window defroster. We won't need it, but it will serve to remind us when we are looking backward. Once we are no longer moving relative to the other clock, the difference stabilizes at negative 7 seconds. As once again we begin the return trip, the clock reading increases when approaching the other clock, and decreases when we leave it behind. In the end, it reads positive 11 seconds, and recalling that before we began the journey, it read negative 3 seconds, we are left with a total change of 14 seconds. To illustrate the source of this final 14-second discrepancy, let's compare the clock inside the car to the outside clock. On the bottom, we will see the car's frame of reference, and on the top, a view from the exterior frame of reference. But at present, they look just the same. For this illustration, the time delay has been removed, allowing us to see everything instantly. Under these circumstances, we can witness time dilation and length contraction directly. Running the top version of events first, we see the car contract while it is moving. It travels the full length of the track and returns. While it is moving, the clock on the car runs slow, so that at the end of the journey, the car's clock is behind the exterior clocks. Now the events as viewed by the car, they're quite different. Centering him on the screen, we see that for him, it is the track that contracts, so the journey is very short, and the time taken according to the car's clock is equally short. The exterior clocks appear to be running fast, because they are once again ahead of the clock on the car. But now we are stationary, everything is the same, top and bottom. and the disagreement between the car's clock and the one beside the track is unmistakable, either way you look at it. Now we consider the delay due to the finite speed of light. It is responsible for our perception of the outside clocks running either fast or slow, depending on our motion relative to the clocks. This illustration, let's imagine we could stand aside and see even light waves instantaneously. If we treat the exterior clock as light, emitting light pulses at 1 second intervals, we see that the moving car intercepts these pulses at various rates. Rapidly when approaching, and slowly when receding. Since at each encounter, the driver would see the clock advance by 1 second, the exterior clock appears to gain time when he approaches, and lose time when he recedes. You may have noticed how the clocks and the landscape appear to warp as we started to move, and also the faster we went. This is the result of the finite light speed that makes the picture appear distorted. This is sometimes referred to as the aberration of light. It's somewhat analogous to driving through rain. Even if rain is falling down, it will appear to someone in a moving car to fall at an angle, striking the windshield from ahead. Light, of course, is coming at us from all directions, not just from above, but once we are moving, most of it appears to come from ahead. The result is to distort the picture we have of objects outside by crowding them together ahead of us. Another phenomenon is the sensation of lurching backwards before starting to move forwards at the beginning of a journey. You surely noticed this in our previous experiment. If we replay the first few moments in slow motion, you can see that the car appears to move backwards. In fact, the start sign comes into view a little before proceeding forwards, whereas it was previously hidden. This occurs because when we accelerate, we encounter light that was emitted from sources that were hidden from us before we began to move. As you can see in this illustration, light from a point at the top of the start sign is not getting to the driver's eyes when he is stationary. As he starts to move forward, some of the light which previously went over him is now brushing the top of his head, briefly coming down to eye level. In this world, light's substantial travel time has strange consequences. Now we take the car to an imaginary city with towering buildings and uniformly straight and level plots. All cross streets that we will encounter are perpendicular to our path, a fact which will be important to remember later on. We'll increase speed slowly to show how quickly the effects of this aberration of light manifest themselves. Notice how the cross streets no longer appear straight, but bend away from us, and the buildings appear to bend. And yet the curve parallel to our path is still as straight as can be. The leading sides of the buildings no longer appear at right angles to the street front, but are angled away from us, forming sharp corners. Look at this open space, a park, to our right. It doesn't appear to be a rectangular plot at all. Taking a glance behind us, we notice that everything looks a little bigger and appears to move much more slowly than did the street in front of us. We've now entered a tunnel. You will encounter several of these along the journey. And note that we are now traveling 27 kilometers per hour, as fast as we dared to go in the last experiment. Let's accelerate and go further into the red. the appearance when looking through a telephoto lens. On the other hand, in front of us, everything appears to be gathered up, just as if we were looking through a distorting wide-angle lens. As we're about to accelerate again, this time looking out the rear window, pay attention to the time. Once we begin accelerating, the tunnel mouth appears to remain almost stationary, as if we were using a zoom lens to keep it in sight. Looking through the front windshield again, notice that you can easily look up the perpendicular side streets without turning your head. You've actually passed these crossroads, although they still appear to be in front of you. As we move through space at a speed comparable to the speed of light, objects and landscapes which we have already passed may still appear to be in front of us, because that is where they were when the light that we see from them was emitted. As an experiment, suppose we place a net curtain down the center of one of the cross streets. We can burst through this without damage. Now we get back in the car. Purple object up ahead is the curtain. Once we are moving towards it, notice it appears to be confined to a semicircle, even though it actually stretches to infinity in all directions. Its circular outline never changes as long as our speed remains constant, but the network of lines on it grow larger as we approach. We freeze as we are about to pass through it. We have reached the center of the cross street as determined by the curtain about to touch the windshield, but it is so distorted that a bulge appears to stretch towards us at eye level, while at ground level, the yellow center line on the cross street is still clearly visible. Let's play that again, this time in slow motion. The aberration of light relates where you perceive an object or event to be to where it actually is. Since length contraction distorts where an object actually is, we relativistic travelers can easily make mistakes about the state of our motion. Right now, everything seems to be moving fast very quickly, much faster, in fact, than the 36 kilometers per hour speed limit. If we were to measure our speed using a street map and our dashboard top, we will conclude that we were going almost 4 times the speed of light. Now, why doesn't the policeman who just passed, you did see him, didn't you? Why doesn't he pull us over? That is because our actual speed is still only 35.5 kilometers per hour. You would think that either our clock or our map must be in error. In fact, for us in the car, it is the reading of distances off the map that is wrong. Length contraction has caused the blocks to shorten to nearly 1/4 their normal length, and that is why we're getting uptown much faster than we might expect. To get back to the policeman, let's take a look at the scene from his point of view. To him, we appear to approach very rapidly, but slow down drastically just as we pass him. Notice how the car appears to be rotating as it passes, as though we were doing a 4-wheel slide, whereas we might appear to warrant a dangerous driving charge. In fact, our speed has not changed at all. The policeman, who is accustomed to these aberrations, relies on his Doppler radar gun, a device which still works admirably, even in this crazy world. To understand what is happening, suppose that there is a series of markers posted every 5 meters down the street, and we release a light signal whenever we pass one. The signals of our progress travel with the speed of light in all directions to whoever may be watching. To assess what was seen by the policeman, notice that as we are approaching, the spheres marking our passage are all bunched up, and consequently he sees us pass the markers in rapid succession, giving the appearance of great speed. After we pass him, the reverse is true. The spheres carrying news of our progress are delayed, making us appear to be travelling much slower than we actually are. And the rotation? This is called Penrose rotation, and to understand it, we have to consider where each part of the car was at the time it sent its contribution to the current picture. You can see in this graph different parts of the image of the moving car are peeling off at different times and travelling towards the eye, all to arrive at the same time. This distorts the picture, making the car appear to be rotating. If the policeman were able to remove the travel time of light and reconstruct the picture as it would appear with instantaneous transmission of information, he would see our speed is constant, our car is contracted, as textbooks say it should be, and if he could see our clock, it would appear to be running very slow, recording 1 second for every 4 on his dashboard clock.
Okay, I think that's enough for today. So next week, second midterm exam. My postdoc will minister that because I want to be here.
Of relativistic travel. Does it know?
And I'll see you in, actually, so in 2 weeks is Easter Monday, but that's a holiday. So I think I'll see you only on the 20.